thank you for attending our third technology session. So today we'll be focusing on additive manufacturing. So this is the agenda for today. So my name is Sarah. I am the Associate Engineer for Cygnas Solutions, and I'll be just giving a short introduction of today's agenda and about Cygnas Solutions. Then I'll pass it on to our Engineering Director, Dr. Ismail Jalisi. He'll be talking about the current additive manufacturing landscape in the energy and emerging industries, and actually about the future of additive manufacturing and its importance and where it's going towards. And then I'll pass it on to Dr. Patrick Mermet, who will talk about simulating additive manufacturing. And he'll discuss case studies about how Simufact can be used to explore and simulate the total additive manufacturing process to predict distortion, residual stress, and failures, to provide guidance on ensuring a quality build the first time, which means that you can save time, save reduced waste, and maximize profitability. And then we'll have time at the end to answer any questions you do have. If you do have questions throughout the presentation, please do just type them out and we'll try our best to answer them as we go along, or else we'll just make sure to answer them all by the end. So we do have a packed schedule today, so I will be giving short warnings for the speakers throughout just to make sure we have time to go through everything. We also do have Huram Kadir, who's the Cygnas Solutions director. He's not presenting today, but he will be more than willing to answer any questions you do have. So I know this is the third time we're doing this, so apologies if you've heard this already, but we always do have new people that come to these presentations, so it's really important to present what Cygnas Solutions does. So Cygnas Solutions is based in Aberdeen, but we do have support resources available all across the UK and globally, where we aim to focus on three main areas, which are engineering consultancy, software, and training. So Cygnas is run by engineers with experience across a vast range of verticals, with specific focus in the aerospace and energy sectors. Our experienced engineers will support you with complex problems and technology adaptation with a view of making your company Industry 4.0 ready. Today, we'll get a chance to discuss more about the key enablers of Industry 4.0, which in this case is additive manufacturing and simulation. We're also proud to be authorized business partners with MSC Hexagon, where with their partnership, we aim to accelerate your company's development and growth. So this is what we aim to bring, and we always make sure it's done with the Hive collaboration values, which is the honesty, innovation, valued focus, and engineering insight. The extensive experience in consultancy and engineering analysis across a range of sectors allows us to strive for innovation and excellence in engineering. A key differentiator with us is that we can help overcome the hurdles in the implementation of Industry 4.0. So if you've been able to attend our previous technology sessions over the few months, you might have already seen this wheel. We try and focus these technology sessions on an expert review of Industry 4.0 ready technologies for the energy and emerging industries. This wheel essentially shows the 9 elements which we believe builds up to be Industry 4.0. Some of you might know this, some of you might have already seen this or been to our previous technology sessions, but just to recap what we've previously discussed is, so our first technology session was actually just an introduction to Industry 4.0, including the industry-leading nonlinear FEA analysis solver MARC and the world's leading CFD technology MSC Cradle. We then focused our second technology session on machine learning and simulation, especially on the Odyssey platform and how machine learning softwares like Luna is able to accelerate design and real-time parametric simulations to reduce time and increase profitability. So in this session, we'll focus on additive manufacturing with the aim of achieving your business goals by replacing time-consuming tests with simulation to shorten time to market, reduce material and energy costs, and increase machine and manpower availability and productivity. So on that note, I'd like to pass it back to Dr. Ismail Jalisi, who will be discussing more about additive manufacturing in the energy sector.
Okay. Hello, hi. Ismail is having some problem signing in, continuing with the team's issues, but continue. So I hope everyone can hear me. So additive manufacturing has been there for a while, but recently there has been technological advances and obviously a need for technologies being more sustainable. So as you know, when we use manufacturing, mostly people have been using subtractive manufacturing, where you're actually removing material and manufacturing many different parts so they can fit. But with additive manufacturing, we can get much more complex shapes, larger, they could be both small and large in size. And by doing additive manufacturing, where we build parts layer by layer using different techniques, you can actually be much more sustainable and reduce the amount of your footprint in terms of CO2 emissions and energy usage, which could be as high as 50%. Compared to, if you compare additive manufacturing to, let's say, your agile manufacturing or AM manufacturing, which is additive manufacturing, as we mentioned, you save labor. There's, you save amount of people, that need to work on that technology. Is much more flexible, and it is scalable and more deployable. The only area that is probably is, let's say, if you're doing mass production at a very high speed rate, that still has not been ready yet. Next slide. Okay, so from the oil and gas energy perspective, there are many areas and applications that can open up. One that we have just mentioned is sustainability, but in regards to also fabrication of complex geometry, replacement of parts, spares, reducing your number of parts that you actually require in an assembly, which could, and hence there is saving there. There are a lot of parts that are, for example, cast and forged parts. We all been there that we have to wait months and months for forged parts or castings, which, in reality could be produced in a very short lead time with high quality results, without waiting for other people to actually send those parts out to you. Next slide. So, areas of interest for oil and gas in these regards and energy sector in general are rapid prototyping, faster product development, unique parts and products. So there are actually parts that one of the key areas here is that when you do AM, people sometimes use them exactly as they would for normal subtractive manufacturing designs. But the reality is that the amount of designs that you can achieve through AM manufacturing is much more diverse, and in fact, you won't be able to manufacture such parts. For example, if there are parts where there are restrictions of the amount you can drill into an object, but with EM, because it's being built layer by layer, you can have very intricate designs, both out on the outside and inside of a machine, which can be beneficial, for example, for cooling channels, or where drill holes, or you need specifically areas where there is a lot of intricate holes within a structure. Next slide. So now we're going to be showing you some examples of what has been achieved in the aerospace sector. This is a company.
For some reason, the video.
It will take a few seconds to load up, Sarah. So we'll show basically how this can be used in the manufacturing of in the other sector that has been already picked up and being used. So this is VAM manufacturing, which basically uses is kind of direct energy method deposition, where you in a deposit weld material and you can then essentially build up layer by layer. Okay, so I'll play this video now and it will show you. So as you can see, you can connect a weld machine to let's say a robot, a KUKA robot, anything. And this is a company called Relativity Space, and you can see how they are building the full. This seems to be a pressure container, but they can actually use it to build whole rocket structures, pressure chambers, and all kind of interesting equipment. So what that shows is that these materials that are used in additive manufacturing are quite robust and can actually be able to take a lot of these pressures and loads that you would expect in let's say oil and gas. The second example is that of using another technique which is called direct metal laser sintering, or which is a kind of a powder based format. So you have powder in a enclosure where then laser is used to build the whole thing layer by layer. This is one of the techniques that is gives the best strength results and has reduced overall stress and higher quality and higher density and less porosity. So is used in high critical applications. The size has been traditionally limited, but now we're getting larger and larger 3D printers. So this again, a company, US-based company called Launcher, that's used 3D manufacturing technology called DLMS and is based on a machine made in Germany. Yeah, so I can show you this quick video as well. And this is just a video of a test of the rocket chamber. Yeah. Okay, so moving on to the next slide. This is again, showing your additive measurement with layer by layer being added. This is again based on direct energy deposition. And you can see how the simulation can be used and to the simulation, you can simulate that to be able to predict your residual stresses and your distortion, which is quite important. And sometimes you need to know how your part needs to look like at the end, and then there is some iteration. So especially for larger parts, it becomes important to be able to simulate it in a virtual environment before you actually manufacture parts, so as not to get the part out of your tolerances that you require. Okay, moving on to the next slide. Yes, so in this regard, we can use two softwares that have been optimized for simulating additive manufacturing processes. Some of the ones that we have just showed you are arc welding, which is VAM, and direct energy deposition. But these are not the only ones that can be simulated. So you can have so the powder bed fusion, which is the one that we showed for the DLMS, that is use powders layers that are then laser sintered on top of each other and then later heat treated. So we're able to simulate using Simufact, welding, and Simufact additive, all of these processes, which is quite important. And these can be, it's essentially they're based on MSc MARC technology, which uses a non-linear FES simulation to be able to simulate the multiphysics of heating, cooling, and even possibly phase changes. Next slide. I'm going. Brilliant. Okay, so welcome, Mr. Patrick Mehmet, and happy to have you here.
I can present now?
Yes.
Yeah. Okay, let's try. Okay, you can see it?
Yeah.
Great. Okay. If there are any issues, let me know. I will start now. Okay.
Great. Thank you.
So yeah, thank you for the introduction. So I'm Patrick Mehmet from Simufact Engineering. We are part of MSc and then of course also part of Hexagon. And I want to talk to you about the quadrature of additive manufacturing. So how to optimize design quality, costs, and time through simulation simultaneously. So just very quickly, a brief introduction to our company. So we are based in Hamburg. We had our 25th anniversary last year. We are a medium-sized company, but we have global business, more than 1,000 customers. So our history is based on the forming simulations. They're one of the most important products we have, but also since 2016, we have the Simufact additive around, which is able to simulate the powder bed fusion processes. There are different names about it, but we call it powder bed fusion. It's a general naming. And also the sintering of metal binder jetting, which in fact is also a powder bed process. In our welding simulation, we can also simulate the metal deposition or direct energy deposition. And what is also under our technical responsibility is the kernel of the MSc Apex generative design, which is very useful to create really innovative designs for additive manufacturing, or which might only be producible with additive manufacturing. So let's go to the topic of today. So we talk about additive manufacturing, but what is the manager's perspective? So they think about cost, quality, time, scope, not necessarily about nice designs. But of course, this is the basis for that. So we have the devil's square here, the devil's square of project management. So we want to achieve the scope of our project. We want to be on time as fast as possible, and we want to have the least costs as possible. To achieve that, simultaneously is maybe not possible. It's a challenge at least. So if you want to have more quality, maybe you need to invest more time and money, or maybe reduce the scope. If you want to reduce the time, you might worsen the quality, live with higher costs, and also reduce the scope. If you have less budget, you will need more time, deliver less quality, and also have shortages on the scope maybe. And when you want to increase the scope of your project, you need to invest more time, more costs, but you have a fallback on quality. So in the end, so let's talk about the metal additive manufacturing process chain. So we concentrate on metals because you need to invest a lot of money to print metal, other than with plastics. So simulation is really worthwhile here. So often you start with a topology optimization to really get a design for additive manufacturing. Or another application is that you do a scanning, an optical scanning for reverse engineering. So for example, for spare parts. So really two completely different applications. But in the end, you need to derive a design out of that, because normally you don't get a final design. So you need some designer to do that for you. And then we have the classical way. You do a static strength and fatigue simulation. And of course, MSc has fantastic tools for that, like Nastran, Mark, CAE, fatigue, and so on. So this is very classical, but also very important. And then what we offer as Simufact is the manufacturing simulation. So maybe something that is underestimated still by some people, but it's not only designing and calculating things, you also need to manufacture it. And a lot of things can go wrong, but with simulation, you can improve that. Then when you're happy with your results, you need to go to a build job preparation. The part needs to be sliced, and you need the hatching patterns of your laser and so on, and there's special software for that to do that. And the nice thing in additive manufacturing that all this is done in a digital virtual way. And that means when you now go on, you will switch into the physical or the real world. So you do the 3D printing, you create the part, you generate the part. Now you're physical. You do a stress relief heat treatment normally. You need to cut off the plate. So you have a base plate in production normally where you print the part upon. You need to remove the supports that are needed for the manufacturing. You need to do a surface finishing, for example, machining, which is quite common, and a quality control. So what does this mean in terms of time and costs? So in the digital world, it's quite easy. You can iterate fast, and this will not cost a lot. But if you need to do that in the physical world, so for example, if your print job does not work, if you get scrap out of the machine and you need to reiterate, this is very, very costly and very, very time consuming. And this is really where simulation helps you, because if you are able to prepare your print in the right way, in the digital thread, then you are done also with the physical world. Okay, so today I will talk about topology optimization, which in our case is the generative design. This one is already covered, so I will not talk.
Sorry, Patrick, just because we're sharing Ismail's screen, do you mind speaking a bit louder? Just because the volume's just decreasing, if you don't mind.
I will speak louder, okay?
Yeah, thank you.
So So this is the classical way. So this is Nastran, Mark, and CAE fatigue. I will not talk about that today. Of course, I will also present to you manufacturing simulation in terms of metal powder bed fusion, metal binder jetting, sintering, and the build-up welding applications. So let's go to the different topics. The main scope. What is the main scope of additive manufacturing? You need a nice design. Yeah, so the innovative design really makes additive manufacturing worthwhile, at least when you create a new part. Of course, it's a different story for spare parts, maybe. Spare parts, you have more like a reverse engineering application. So this is a nice example for a generatively designed part. And what are the objectives and the goals? You normally want to achieve lightweighting, you want to be efficient, you want to reduce time to market, and of course you want to reduce costs. In this case, there was a 63% weight reduction compared to the original design. Reduced fixation points to 4. I think there were 5 or 6 in the original design. You have one integrated part design, which of course helps in lightweighting. And what is really the clue, this part, as you see it here, has been designed in only 3 hours. Yeah, so you don't need a designer that is doing that for you. The software gives you the final part that can be printed. So what are the disadvantages of the classical topology optimization? You do not get clear designs. Yeah, you do not get stresses, and it's hard to interpret what to do with your results. You don't have a sufficient resolution. You get a density field and not really a design. Sometimes you get some senseless results, for example, like this, an incomplete connection. And you have these wrecked surfaces, yeah, and that is the reason why you need a designer in between to interpret your result and make a design out of your topology optimization result. And this is different in the generative design. So in this innovative approach, you have a design evolution during the optimization, you have an iterative refinement, and in the end you have a fine smoothened mesh, and you can also export a generic CAD format. Yeah. And what is the difference? In classic topology optimization, you don't have a design as a result, you have a density field. You have no stress information, or at least no reliable stress information. And in this case, the stiffness is the target, not the weight. That is the reason why weight is normally reduced by 50%, because people give this as a target, but it's not really a result. In the innovative topology optimization, which we call generative design, you have a final printable design. It's already stress optimized. It's weight optimized in the sense that automatically the least weight is achieved, and it's far quicker. So, and of course, this will help you to reduce the cost by the generative design, because in existing software, or you need different softwares for the mesh generation, optimization, and then again for the smoothing of the part, geometry retransition, verification. So you need to go back and forth, maybe you need different people doing that, and they spend a lot of time. With MSc Apex generative design, you have all that in one tool, and you can do it very, very quickly. So the reasons for that is that you have an automation, you get the maximum lightweighting, you achieve really a dramatic time reduction, and this all helps you to save money. So let's have a closer look. So if we look at calculation times, for example, the kernel has been developed for GPUs. So this is the fastest way. And in this example, it was possible to get this final part in only 28 minutes. Of course, not everybody has the same hardware. So maybe you don't have a GPU, you have a CPU, but even then, it's in this case like 3 hours. Yeah, so it's compared to other technology very, very fast, because it's completely automatic. You just start it, and after 3 hours, you have your result print ready. Why is it called generative design and not just topology optimization? Because you can derive very quickly different variants of your design. So here's just an example for that. So you can even each design is fulfilling your requirements, but you can even select, let's say, your preference here. And this is what we call the design funnel. So you have a lot of designs which fulfill your stress requirements, for example. But maybe you have other requirements like weight. So maybe you want to select the least weight part. Also, the design itself. So how does it look might be a requirement. For example, if you can see the part, an exterior part. And also what part is better to be manufactured. So in the end, out of a lot of designs, you can select really the most appropriate one for you. And this is done all in an MSc Apex generative design. So it's really one seamless optimization workflow from CAD to CAD. So just a graphical example here. You can do all the CAD import manipulation here, including the design space. You get the results and also the CAD export in the end in one tool. So this is what we call an end-to-end process, and yeah, we don't need to go into all the points here. But what we covered is the beginning here from 1 to 5. You can do everything in the MSc Apex generative design. Then you have your print-ready part. But then there's another step, which we call manufacturing validation. So this is the next point I will talk about. And this is done with Simufact additive. And then, of course, you can also do a final design validation with Nastran, for example. You already have a stress optimized part, but we call it like a pre-assessment, and the final assessment is not necessary, but is a good idea to really have, let's say, Nastran results and not topology optimization results. Okay, let's have a look at some use cases. So this is a wheel carrier from a Formula One student car, I need to mention. And this one has been designed in only fully automated, fully optimized. So really, really quick. This one is a really nice example. So we have a satellite bracket, and on the picture you see the original design first. It's a mounting of drives for regulating microwave filters on a communication satellite. So the original design was machined aluminium. And also you see the design space here that was used for the topology optimization. And in the end, you got this part that has been additively manufactured in laser powder bed fusion. The aluminium alloy is different, of course, because you have another process, and it's a classical, but it's a typical AM alloy, aluminium, silicon, 10 magnesium, that has been used here. And you see the benefits on the left. You have 55% weight reduction compared to the original design. On top, you have 31% stress reduction, though you have not even half of the weight. And also you have 79% of stiffness increase. Yeah, so all the parameters have been improved by the optimization. Another example comes from automotive. So this is a bonnet hinge. And here we have a 70% weight reduction, which is really unbelievable. The classical optimization only achieved 50%. So that means if you calculate a little bit, it's 40% more lightweight than the conventional optimization. And also the comparison of the engineering time was done, and you save 60% of the time in engineering, which are, of course, also the main costs to get this design. Then we have this diode arm for chip manufacturing. The main target was not really weight reduction, but when you have these optimizations, you have a lot of side effects, as we have seen before. So you have a weight reduction, but on top, you have the stiffness increase, incredible 400%. And that, of course, also leads to an increase of the first eigenfrequency. Yeah, so this is really much, let's say, much more stable in production, and because you need, of course, a high accuracy for these diode arms. And also side effect, it's easy to clean, so you have a smooth surface, so you do not have any undercuts where dirt might be collected. Okay, I think this is the final one. We have a gripper for packaging machine. Again, 56% weight reduction, very nice, 4 times stiffer. But what is really crazy here, it's only 18-minute calculation time. So it's really very fast, and you get this final design without having a designer that needs to interpret your result. Okay. Now let's assume we have the design. So either we have generated the design, or we have scanned the design maybe, because we need to produce a spare part. And now our advice is simulate before you manufacture. So this can be done with Simufact Additive. And what are the key capabilities and benefits of Simufact Additive? In additive manufacturing, it's very crucial how your build orientation is, and the software provides a quick assessment of all possible orientations, and you could select the most appropriate one according to your requirements. You have an embedded cost estimation, so you can also optimize versus the production costs, or give a quote, for example. The meshing is absolutely fast and reliable. So in additive manufacturing, and we have seen that before, you have complex filigree parts most of the time. We use this voxel meshing with some technical tricks in the background to make it numerically reliable. So it's just pressing a button and everything is meshed quickly and automatic and reliable. So it's not possible that the meshing fails like in other cases. Support structures are a very important topic in additive manufacturing. You can create support structures with the software, and you can optimize them, of course, also simulate, assess, and so on. Which processes are we looking at? As already mentioned, metal powder bed and metal binder jetting sintering. And what are the results? What is the outcome? So you can predict the distortion, and what is even more important, you can compensate it in a very nice way. So you can print your parts straight, instead of having distorted parts out of the machine. You can assess the manufacturing risks, identify failures and crashes, and mitigate them before you print. So stay in the virtual world, optimize the print, and then go to the real world. And also you have a look at the process chain. So it's not only printing a part, you have a lot of post-processing steps that you need to consider, like the stress relief, heat treatment, cutting from the plate, support removal, and so on. And all this is covered by the software. So very quickly, we go through the different criteria here. So we have the build orientation assistant, that you can optimize your print or your print orientation versus supported area or the support volume, because you need to print and remove everything regarding the support. So it's additional effort you want to minimize. You can minimize the projected area to put as many parts as possible into the machine. Design height and costs can be minimized, or also local minima, that if you want to avoid that. So you have a very intuitive interface here to select really the most appropriate orientation. Embedded cost estimation has been developed with customers that are doing production, and this really helps you also to optimize against costs, not only quality. So in the metal powder bed fusion, there are different ways to simulate. And one, or the most popular way, is what we call the mechanical simulation, which sounds a little bit strange because we have a thermal driven process, but you can reduce this to a mechanical problem, and that makes a simulation really fast. But still the results are very good and reliable. You can see this on the slides. On the left side, you have simulation results. On the right side, you have measurement results, and they are matching really well. And also on the bottom middle part, you see a correlation between measuring points which is really, really nice between the simulation and the measurement. So it's a very reliable way to simulate. Calculation times are typically dependent on the model, of course, some minutes, few hours, not more. But there's another way to simulate this type of additive manufacturing. You can do a thermal simulation to get an insight into the global thermal management of your production. And also you can do a thermomechanical coupled simulation, which is a different approach. It will take more time, of course, but you get a deeper insight. And also you can do things like phase transformation here, for example, and get a better understanding of your printing process. So both methods are suitable to identify manufacturing risks. And what people fear most is a ricotta crash. So you need, you have these ricotta blades that are applying the powder layer by layer. And if it crashes with an already produced part, then your production stops. And that is really the worst case scenario. This can be predicted by the software. Also things like part or support failures, which are stress or strain driven, can be assessed and mitigated before you print. When you look at the subsequent process chain, some examples here. For example, stress relief heat treatment, of course, you have a significant stress reduction, but in a lot of times you still have some stresses. And when you cut off the plate on the bottom part, you have an additional stress reduction, which is linked, of course, to an additional deformation. Yeah? And you need to know that before you print. And you can also compensate that. So you can compensate in a way that after removing the part from the plate, it is straight and it is within your tolerance. It is a really very nice application. Support removal can have an influence on your part. Not really on this one because it's quite stiff, but it can. And also but that is more an aerospace application, maybe hot isostatic pressing has another influence on the distortion, on the stresses, and of course on the densification of the part. This can also be simulated.
Apologies, Patrick. I know we started late, but if it's all right, we just have 5 minutes left from your presentation, just so we have enough time to answer any questions at the end, if that's okay.
Yeah, try to be quick.
I think there are not that many questions, so yeah, just you know, take it. You know, no need to hurry too much. It's fine. Yes.
Okay. So by the latest release, we have introduced also a machining a simulation, which is funny because we have an additive manufacturing and of course included a subtractive manufacturing, but it's a typical post-processing step that can also be simulated. And in metal binder jetting, we have the sintering simulation. So metal binder jetting, you do not have a laser that is melting particles, but you have a binder agent that is binding the powder particles. That means you have a sintering step afterwards. And during the sintering, you have a very high densification of the part. You have a high shrinkage. But the shrinkage is not uniform, and that means you get a distortion while it shrinks. And this is also a challenge, but you can address this with simulation. So we can see the videos here, how the part shrinks, and this is unscaled, so it's scale 1. So you have like a 30 to 50% shrinkage. You can predict that, and you can also do a compensation for this. So this distortion compensation is really like the killer functionality of the software. You can do it in an automatic iterative way, which really gives very good results. You can almost drive your distortion to 0 by applying localized pre-distortion to your part. Okay, when we now have a look at the generative design in combination with the manufacturing simulation, then the generative design might put out a lot of suitable designs. Yeah, but then you can do the manufacturing assessment, and maybe some designs are not as suitable as others. So you make a pre-selection here. And then the final selection can be on price. Yeah, so of course you use a part that is fulfilling your requirements, that is manufacturable, and that has the least cost. Yeah, so in the end, you really get an optimized part, not only in terms of functionality, but also in terms of costs. So yeah, this is a very generic return on investment example. That, for example, if you use the software and you can avoid a lot of crashes or a lot of quality issues, then a return on investment within 1 year is the normal case and not the exception. Okay, let's talk a little bit also about direct energy deposition. I think Kura mentioned that at the beginning. You can do that with our welding software. Of course, calculation times can be very long still, but the modeling time has been reduced drastically. So you can import just G-code and the model is set up more or less automatically, like we can hear. So you have an automatic geometry creation, an automatic meshing, automatic model setup. And when you have the simulation results like here, you can also do the distortion compensation for the build-up welding, for the direct energy deposition. You can translate this again into a G-code, go to the machine and print it, and have this kind of optimized part, or maybe optimized manufacturing in this case. And how does this help? So we see an optical measurement here. We have the original printed part on the left, and you see some mentionable deviation, yeah, between the printed part and the CAD. All this can be managed by using additional material and machining. But you can see on the right side, if you do the distortion compensation, the part is much better within the tolerances. So anyway, you need to do machining, but when you do the compensation, then you can really reduce your material allowance, you can minimize your machining effort, and again, you save time and money. So this is really an issue in the build-up welding. Okay, this was a funded project, so some acknowledgement here. I am through. So many thanks. Vielen Dank, as we say in German, and I'm open to questions.
Sorry. Thank you, Patrick and Herm, for the presentation. We're just going to wait a few minutes to see if there are any questions that come in. So I hope during the presentation you got an idea to see how by simulating additive manufacturing through software such as Simufact, you can predict performance and optimize the build process to save time, reduce waste and maximize profitability. And by leveraging simulation, data, and even metrology, you can increase the robustness and reliability in the manufacturing process. So where does Cygnas Solutions as a company comes in? We can essentially, along with MSC Hexagon, help you optimize your additive manufacturing process. So we can help you overcome those hurdles and to implement, including your CAE, material selection, manufacturing, and quality assurance. So we can help you guide you with that optimization. On that note, if there are any questions, please do ask them.
Okay, perfect. So yes, I've sent the screen live with our contact details. We are authorized business partner with Hexagon, and we work closely to bring MSC software, which is part of Hexagon, and not only that, but other softwares like Hexagon has many verticals. So one of them is PPM as well. So what we do is that we're local partners based in Aberdeen and London, and we work with both our clients and Hexagon to bring the best solutions, not in terms of, if companies want to use the tools, so software sales, as well as if they, they're interested maybe to try out the technology or need consulting support on these things. We, Cygnas work closely with all of our technology partners to be able to provide solutions that help our clients to achieve their goals and targets in the most efficient way. So I think at this time, we would like to thank all our attendees who attended our live event, and we look forward to hearing from you guys and answering any more questions, which you can forward us to solutions@cygnas.co.uk. Thank you very much again to our guest, Mr. Patrick, to coming in and enlightening our audience with all these key informations and how generative design, additive manufacturing, and the key technologies that are being used across the industry to add value and realization to different organizations around the world. Thank you again, everyone, for joining us. That brings us to end to our Cygnas Technology session today.